So here we want to evaluate the limit as x approaches 0 from the right of x to the power of the natural log of 2 divided by 1 plus the natural log of x. And so at first this seems like a pretty complicated limit, but the first thing that you should always try when evaluating a limit is just see what happens when you plug in the value of x that you are approaching. In this case, that would be 0. Now it doesn't matter that x is approaching 0 from the right, we can still plug 0 into this expression for each x and see what kind of result we get. Depending on that result, we can either conclude what the value of this limit is, or we may need to make some adjustments if we get something like an indeterminate form. And so let's see what happens. Let's plug 0 in for each x in this expression. If we do that, we'll find that this is equal to 0 to the power of the natural log of 2 divided by 1 plus the natural log of 0. Now, when we go to simplify this, we're going to encounter a problem because the natural log of 0 is an undefined value. If you plug the natural log of 0 into your calculator, it will either tell you it's undefined or it will give you an error. And that's because the natural log function is not defined for 0. It's only defined for positive values of x greater than 0. And you could see that if you were to look at the graph of the natural log function. If this is the y-axis, and this is the x-axis, the natural log function looks something like this. That would be y equals the natural log of x. The function will get closer and closer to the value of x equals 0, but it will never reach it. The natural log function is not defined for x equals 0. Okay, and so how do we deal with this natural log of 0 in the denominator of this exponent? Well, you have to remember what's actually going on here with this limit. Remember that we are looking at what happens as x approaches 0 from the right, not what is happening at x equals 0, okay? So we're not looking at the natural log of 0 per se. We're looking at what happens as you take the natural log of values of x getting closer to 0 from the right. And if we were to look at the graph of the natural log function, we can answer the question of what is happening as x approaches 0 from the right. As we get closer to 0 from the right side of the function, the y value is getting smaller and smaller. Or another way to view it is that it's getting larger in the negative direction. Okay, so we would say that the natural log of 0 is getting closer and closer to negative infinity. The y value is getting smaller. So in the denominator, we have 1 plus negative infinity, or a value that is decreasing, and adding 1 to a decreasing value is not going to affect that decreasing value. So then what we could say is that this is equal to 0 to the power of the natural log of 2 divided by negative infinity. All right, but now what about the natural log of 2 divided by negative infinity? What can we say about that? Well, we'd have to look at a couple calculations, but in general, when you have a fixed value or a finite value divided by an infinite value, we say that the result would be 0. Because as you divide this fixed value of the natural log of 2 by smaller and smaller numbers, or bigger numbers in the negative direction, the resulting value will get closer and closer to 0. And just a couple values to show you what I'm talking about. The natural log of 2 divided by negative 1 would be equal to negative 0.69 and some more decimals. And then the natural log of 2 divided by negative 10 would be equal to negative 0.069 and some more decimals. And you can see that as that denominator gets smaller, the result is going to get closer and closer to 0. Okay, and you could continue to check that for more values in the denominator. You could take the natural log of 2 divided by negative 100, and you'll get another value that is even closer to 0. Okay, they're negative values, but they are still getting closer to 0. So what we can conclude here is that the natural log of 2 divided by negative infinity is going to approach 0. As that denominator gets smaller, or as our values of x get closer to 0 from the right, the natural log of 2 divided by this denominator will become 0. So what we're left with here is 0 to the power of 0. And that right there is an indeterminate form for our limit. You cannot take 0 to the power of 0. As much as it is tempting to say that it's equal to 1, because we say that anything to the power of 0 is 1, that's not true for 0. All right, any other finite value to the power of 0 would be 1. But 0 to the power of 0, we don't know what that is. That's an undefined value. So what we have to do is make an adjustment to our limit such that we can evaluate it. We cannot evaluate it in its current state. We have to change it in some way. And so how can we adjust this limit? What kind of changes can we make to this limit so that we can evaluate it? Well, a trick to be aware of when you get an indeterminate form of 0 to the power of 0 is to make use of the natural log function. What we're going to do is set this limit equal to another variable, let's say y. Okay, so here's what I'm going to do. I'm going to let y equal the limit as x approaches 0 from the right of x to the power of the natural log of 2 divided by 1 plus the natural log of x. Now what that's going to allow me to do is take the natural log of both sides of this equation and then use one of the properties of logarithms to make the limit easier to evaluate. And you'll see what I mean in just a second. Let's just take the natural log of both sides of this equation. That will give us the natural log of y is equal to the limit as x approaches 0 from the right of the natural log of x to the power of the natural log of 2 divided by 1 plus the natural log of x. Now, technically, we are taking the natural log of the entire limit, right? We would take the natural log of this entire expression. But one of the properties of limits is that whatever operation you were performing to it, you could also just perform it to the actual expression in the limit. Okay, so taking the natural log of the limit as x approaches 0 from the right of this expression is the same as the limit of the natural log of that expression. Okay, I hope that makes sense in case you were wondering why the natural log is not also around the limit notation itself. We can do that because of the properties of limits. Okay, but back to what we're doing here. Why is this helpful? Right? Why is taking the natural log of both sides of this equation going to help us make the limit easier to solve? Well, what we can do is make use of a property of logarithms that when you have a logarithm of a value to a power, you can take that power and multiply it by the natural log. All right, so here's what I'm talking about. Here's what we can write. We can say that the natural log of y would be equal to the limit as x approaches 0 from the right of the natural log of 2 divided by 1 plus the natural log of x times the natural log of x. Okay, so here's what's going on here. We use the rule of logarithms that the log of a to the power of b is equal to b times the log of a. All right, that doesn't just apply to the natural log function, it applies to all logarithmic functions. I'm just using the natural log here because it's easier to work with. In general, if you have the log of a value raised to a power, you can bring that power out front and multiply it by the natural log, and then just have the natural log of a. You keep the base of that exponential expression inside the natural log function. And that's exactly what we did right here. We took this exponent of x and brought it out front of the natural log function, and so we just have that exponent multiplied by the natural log of x. And so that exponent is no longer an exponent, it's just a rational expression being multiplied by the natural log. Or you could think of it as just a fraction being multiplied by the natural log of x. Okay, and so that is going to make our limit easier to evaluate. All right, because now what we're left with is the limit as x approaches 0 from the right of the natural log of 2 divided by 1 plus the natural log of x times the natural log of x. And so we could simplify this a little bit by multiplying the natural log of x into the numerator. We could just multiply it by the natural log of 2. And so we would have the natural log of y is equal to the limit as x approaches 0 from the right of the natural log of 2 times the natural log of x divided by 1 plus the natural log of x. And now what I think we should try is see what happens when we try to plug 0 into this limit. Let's see what the evaluation of that would be. So if we do that, we'll have the natural log of y is equal to the natural log of 2 times the natural log of 0 divided by 1 plus the natural log of 0. Now, we just plugged 0 in for these two x's. That's how we got this expression. But if you remember our discussion from earlier, the natural log of 0 is an undefined value. We saw that as x approaches 0 from the right, the natural log function gets smaller and smaller towards negative infinity. So this right here becomes the natural log of 2 times a negative infinity, and multiplying negative infinity by some constant value does not affect it. Okay, you still have a decreasing value. Doesn't matter if you're multiplying anything by it. It's still going to get smaller. So this would be equal to negative infinity divided by negative infinity. 1 plus negative infinity, or a decreasing value, is still going to be a decreasing value, or negative infinity. So what we're left with here is another indeterminate form for our limit, negative infinity divided by negative infinity. Technically, you could cancel out those negative signs, and you would have infinity divided by infinity, and that is still an indeterminate form. And so it seems like we didn't actually help ourselves at all here, right? We still have a limit that's in an indeterminate form. However, this indeterminate form is compatible with L'Hopital's rule. 0 to the power of 0 is not. That is not an indeterminate form for a limit where you can use L'Hopital's rule. But infinity divided by infinity, that is. So we did actually end up helping ourselves after all. What we can now do is use L'Hopital's rule on this limit, and hopefully that will make it simpler in a way that we can then evaluate it. Okay, so it's good that we check this. It's good to know that we have an indeterminate form compatible with L'Hopital's rule. Now let's actually use L'Hopital's rule. And so to make use of L'Hopital's rule, what we have to do is take the derivative of the numerator and denominator separately for this limit. Okay, we're not using the quotient rule here. We're just taking the derivative of the numerator and denominator separately. It's what a lot of people think the quotient rule should be when it's actually not. Okay, so let's take these derivatives here. We'll have the natural log of y is equal to the limit as x approaches 0 from the right, and we are taking the derivative with respect to x of the numerator and denominator separately. And so let's start with the numerator. The natural log of 2 is just the coefficient or the constant multiple of the natural log of x. So we're just going to be multiplying the natural log of 2 by whatever the derivative of the natural log of x is. Now the derivative of the natural log of x is a fairly simple derivative. It's just 1 divided by x. So what we're left with in the numerator is the natural log of 2 times 1 divided by x. And then in the denominator, we have the derivative of 1, which is 0. The derivative of all constants is 0. And then the derivative of the natural log of x, once again, is 1 divided by x. So we have 0 plus 1 divided by x, which gives us 1 divided by x in the denominator. And now something very interesting happens here. Notice that we have 1 divided by x in the numerator and the denominator. We can cancel them out. Anything divided by itself is just 1, so we can cancel them out and multiply 1 by the natural log of 2, and that's all that's left in our limit. So what we have here is the natural log of y is equal to the limit as x approaches 0 from the right of the natural log of 2. But the natural log of 2 is just a constant, right? There's no variables in that expression. It's not the natural log of 2 times x. It's just the natural log of 2. And the limit of any constant is just equal to that constant. So this changes from being the natural log of y of the limit as x approaches 0 from the right of the natural log of 2 to just the natural log of y equals the natural log of 2. And so we're almost done here. Here's the conclusion that we can make. We now know that the natural log of y is equal to the natural log of 2. And even though we solved this limit, it's just the natural log of 2, that is not the actual limit that we were trying to solve originally, right? Our original limit, this one right here, we set that equal to y. So the evaluation that we are trying to find here, or the solution that we are trying to find, is the actual value of y. So we need to solve for y in this equation, and then we're done. Then we have the value of this limit. Now, you could use a little bit of intuition here and see that if we have the natural log of y is equal to the natural log of 2, in order for this to be true, y would have to be equal to 2. But if you don't see that, that's fine. We can just make use of the exponential function e, which is the inverse function of the natural log function, and that will allow us to solve for y. All right, so here's what that looks like. We'll make each side of the equation the power of e. So we'll have e to the power of the natural log of y is equal to e to the power of the natural log of 2. And since e and the natural log are inverse functions, they cancel each other out and will just leave us with what is inside the natural log function. So we will just be left with y is equal to 2. And so that's our conclusion. 2 is the evaluation of this limit. The limit as x approaches 0 from the right of x to the power of the natural log of 2 divided by 1 plus the natural log of x is 2. That is our final answer. Okay, so that's how you can make use of logarithms to help you solve a limit that is in an indeterminate form of 0 to the power of 0. The properties of logarithms allow us to manipulate our limit in such a way that it was easier to solve and then we could just backtrack our steps to figure out the actual evaluation of our original limit. Okay, and so that's it for this limit. If you have any questions, feel free to leave those in the comments. But if you don't have any questions and you found this video to be helpful, feel free to check out some of my other Calculus 2 videos that are available on my channel. I have an entire playlist full of my Calculus 2 videos, and so if that's something that interests you, I would encourage you to go ahead and check that out. But with that, that is all I had for this video, so I'll see you next time.